there it is. So we're going to take a look at in your homework numbers 9 and 12, and then we can loop around if we need to. Number 9 asks you to rotate this region, which I've sketched here. That's your first move. You always want to sketch this around the axis that we're doing. And since we don't have any other tools to work with right now, we're going to learn another tool today. But since we don't have anything else, what I would suggest you do is if you want to use a disc or a washer, you want your rectangle to be perpendicular to the axis of rotation. Imagine what happens when I rotate this rectangle around. When I rotate it around the y-axis, this is going to produce something that looks like that. It's the best I can do. I know my sketches aren't the greatest, but it hopefully gets the message across. The next thing you want to do, once you have that sketch, I guess I'm going to put this here just to remind myself, delta y is the small side of that rectangle. And so delta y will be the thickness of my little washer, this disc that I'm going to be, well, disc with a hole in it. Let me see, do I have, oh, I do. Got one here. I've got some more for today's lesson. But so I've got this thing, and the thickness is delta y, so this thickness here. So now I have to figure out how big is the whole circle, so the outside, and also how big is this hole. And you can do this either in 2 stages or in 1. It doesn't matter to me. So what I'll do here is on here, I will write down, here's the axis. Anyway, this distance from the center to the inside of the hole, that doesn't show up well, does it? Well, that's what it is. Okay, so that distance up here will be this distance. So you see, transferring it up to the graph is always helpful. So I want to know that distance from the y-axis to this curve. Well, that's going to be this curve, which is x equals y squared. Technically, this distance is x, but because I'm doing everything in terms of y, I need to write this as y squared. So whatever y is, we're going to square it, and that's going to be the size of the hole. Now let's do the outside. I'll change colors. So this distance from the center to that is this distance here. And once again, I need to write this in terms of y. So I have x is equal to 2y. So that's going to be 2y there. And on here, this is 2y. So on your quiz, I'm really focused on getting things set up. In fact, the very last question is to write down the integral. And that's it. I don't have you do the integral. So I'm interested in this part. Drawing, sketching, making your integral. So the next step, let's actually compute the volume of this washer. So the volume of this one washer, we won't worry about the whole thing for now. The volume of this one washer is going to be pi times the outside squared times the thickness. So that's the whole disk. If you imagine if this thing didn't have a hole in it, then this thing would be pi times the outer radius squared times the thickness. But then, of course, we're going to subtract off that hole, which is pi times the inner radius squared times the thickness. So that's actually one of the questions here. One of the questions is, write down the formula for the disc or washer that would result from revolving that rectangle. So basically it's this. And then we have to figure out limits of integration. So let's figure that out. And I think we can see that these intersect here at 0, but where do they intersect there? So we're going to set those equal to one another. 2y is equal to y squared. That means y squared minus 2y equals 0. Or y times y minus 2 is 0. So y equals 0 and y equals 2. So apparently that's y equals 2. So those will be the limits, 0 to 2. And then the final step is to write this in terms of in terms of the integral. So this will be pi times I'll just write it like, well, here, we can handle this, can't we? Times 4y squared, because when you square that, you'll get 4, and you square this, and you get y squared. This becomes dy. And like I said, this can either be as a single integral or as two separate integrals, y to the 4th dy. So there it is in one thing. I hope, I shouldn't say that I'm confident, but well, I'm pretty confident. I'm pretty confident that most of you could do this at this point. Nice polynomial, easy, y to the 5th over 5. This is y cubed over 3, and plug in the limits. Just to show you one last thing, it is not necessary to write two separate integrals. You could do this and write this down as a single integral. So I suppose that it might be better to move this over and move this over. So that's totally acceptable. You could factor out the pi if you want, whatever. So, so that's that one. So are there any questions about number 9 before we look at number 12? So 9 looks okay. It doesn't look terrible. All right. So now, at least now that you see how it's done, I know you're more comfortable when the rectangles look like this, when it's up and down instead of sideways. Sideways, it's hard. It's hard to do this. It's understandable. So just, work with us so we can do it. Okay, next, let's take a look at 12 just to see how that works. Give me a minute. I didn't pre-sketch. I should have sketched this thing. So y equals x cubed. Give me a sec. I'll just do my best. So y equals x cubed looks something like this. Y equals 1 looks something like this. X equals 2. Huh. Okay. I guess I didn't think ahead. Give me a sec. I'm going to redraw. Sorry. I didn't realize that's where we were going with this. So should have looked ahead. Here's y equals 1. And then here's x equals 2. So that delineates this little region here. There. By the way, these two things intersect at the point 1, 1. So, and I suppose we could write down this just for fun. This is the point 2, 8, just if we need it. You could figure out both of those by just solving set y or x cubed equal to 1 and solve. You can figure it out. Okay, so far so good. We've got our region. Now here's the thing that gets difficult with number 12 is they want you to rotate this around the line y equals -3. What in the world? Okay, well, let's go down here to y equals -3. So that's what we're rotating around. So bear with me. Let's go through the process. We've sketched our graph. Next step is to draw a little rectangle. And then imagine doing that rotation, rotating that. You're going to end up with something big, tall, skinny. It's going to be a ring. There we go. Good enough. That's pretty good. But you can imagine, it's not going to look like this. It's going to be a really skinny, I don't think either of my rings looks like what this looks like. It's closer to this one. So this one's a little bit more like it because it's got the hole is huge. You're rotating, the axis is so far away from that rectangle that you've got this gigantic hole in the middle of this ring. Okay, so let's see if we can work this out. This is going to be delta x. So that's the thickness of this thing. So here's the hard part is we have to think in terms of the size of this hole. So this hole is going to be this distance. And that's actually not terrible, is it? You can figure out how far that is, isn't it? It's constant. No matter where you are in this region, the distance between here and here is always 4, right? So that's the easy one. That's going to be 4. So that'll just put a 4 there. The harder one is how far it is from here all the way up to this line. But I think we can do this. So let me make a different color for this. How about that? Let's see, does that different enough? So that distance is the same. It's going to be this distance here. Okay, good enough. You get the picture. So from the center up to the rim, the outside rim. So that distance is going to be from here to here. So that is just x cubed. So from the x-axis up to there, I should label that, shouldn't I? Let me label this. This is the x-axis. So here, this distance is x cubed. This distance is 3. And so you just add those together. Whoops, what happened to my, here we go. So this whole distance is going to be x cubed plus 3. So let me pause, see if anyone's lost their minds. What do you think, Hayden? Mm-hmm. Whoa, wait, are we rotating? Yeah, y equals 3. Okay, so yeah. So yeah, we're measuring the y. You're right. We're measuring the y. So here, from here to here, this is y equals -3. So that'll be 3. And then when you go from here to here, y equals 1. So you add in an extra 1. So I know you knew that already. It's this other one that's problematic. So we'll do the same thing for the one on the right. Start off with the 3 down here. And then here, you're measuring the y distance. And it turns out that the y distance to the top here is y equals x cubed. So that's why it's y equals x cubed for that distance. But you are right. Up-down distance is a y value, but I need to write these things in terms of x because the delta here, delta x, is my small side. So whatever you have for the small side of your rectangle, that's what the variable should be that you're going to write all this. Okay, so once we've got that over this, hopefully we can move on. We can do the actual integral. So this is, oh, I should do the volume first. Let's do the volume and then we'll do the integral. So volume is going to be pi times the radius, the outer radius squared, delta x, plus pi minus pi times the inner radius squared, delta x. And so here we can write this like this, pi times x cubed plus 3 squared minus pi times 16 dx. Or you could write this as 2 separate integrals, I don't care, but that's the way this is going to look. I think limits. I forgot my limits. The limits are obvious here though, aren't they? Yeah, it's from 1 to 2, because these are values of x. So x goes from, x goes from 1 to x equals 2. So that's what this should look like when you get done with the integral. Now, of course, you still have to do the calculus of the integration, but I'm going to trust that you can do that. I know that my trust is misplaced for some of you, but it's something you're going to be practicing and working on before next weekend, right? All right. So anything else about number 12 that didn't get explained properly or that you're just still confused about? Okay, so let's see if we can do this relatively quickly. There are a few others that you did. Were any of the others problematic in terms of setting them up? Maybe you're not sure what the graph looks like or where the delta x or y goes. We can try to straighten things out. All right, if not, I do have one, and it's basically similar to what I just did in the sense that you're not going to do the final answer. You're going to just draw the region, sketch a rectangle, draw the, try to figure out the volume using an integral. So let me give you this, and then, so we'll start at the front today. I'll try to alternate. Yeah, do I want to collect this? I guess I'll collect it today. I'm going to change gears starting, I don't know, Wednesday. I'll tell you tomorrow about how to deal with homework. Because I have one student who was photocopying their notebook. They didn't want to give me their notebook. And I thought, I don't want to make you pay money to hand in homework. So I've got something else I'm going to do starting Wednesday. I'll let you know tomorrow, so you know. But yeah, you can pass that in, I guess. I'm not thrilled about collecting papers, but I'll do it. There's probably too many there. You can pass one back to Thomas. There's a couple. There may be too many. I don't know. I think there's two there. There. Got some. I know you need two more, don't you? There's two more, and you need an extra one. They're perfect. And there's three more. All right. I'll just start making a stack somewhere. Here, we'll put the stack up here. I'll get it in a minute. Don't worry. Oh, did you not get one? Oh, he's hogging them. Okay, come on, Simon. All right. Excellent. Good job. Oh, excellent. I was kind of hoping there'd be an extra. I'll put it up on the screen. Yeah, let me deal with this. Okay. Okay. So just to remind you, you don't have to compute the final answer. I just want the setup. So sketch and follow the instructions. Hopefully you can get it done. Oh, when you're satisfied with your answer, feel free to send it over towards the middle. I'll go gather homeworks up if I haven't got them yet, and I can get the quizzes. All right, beautiful. Wow, front row. Good job. Oh, is this homework?
Oh, yes.
Okay. And this is as well. Oh, and that is as well. You guys just don't want to pile it up for me. Remember, you don't have to evaluate the integral. You're just setting it up, going through the steps. I thought that would make it easier for me to award partial credit if necessary. Thank you. Lovely. You want me to take that as well? It's so beautiful. Very nice. Yes. You happy with that? All right. Oh, look, you decided to go all the way. Very nice. Nice. Excellent. All right. All right, I'm not rushing you, am I? Well, you've got answers. That's good. All right, hopefully you're coming down the home stretch. I'll need to collect them in just about a minute, so try to polish things off so that give me some sort of integral. Thank you. Nice. Thank you. Yeah, go right ahead. Yeah, all right, good job. Nice. Wow, what in the world? All set? Okay. This row. Set. All right, good job. Nice. See these guys. All right, you got something? Nice. Got something. Very good. I like your drawings. I'm loving all these pictures. They look great. You got something? Something? All right, good. Just going to put that final. Now, technically, if this is your answer, you could just put a little arrow up there.
Oh, yeah.
Yeah. So if you just don't rewrite it. That's fine. Yeah, good. Good job.
I wasn't understanding how you're supposed to find product. Like when you set it up equal to. You know what I'm talking about?
The limits.
Oh, I literally did it.
Oh, did you want to circle it as being done? Just,
Like, is up here, x equals.
yeah, yeah. Put a little box and put an arrow. That's fine. Yeah, good job. Don't cross that out. It's right. All right. All right. You got something? Final integral. Nice. Looks good. Yeah. You've got an integral. What are you complaining about?
I like to
You're just meditating. I know. And you got a good integral too. Look at you. All right, I think I've got them all. Anyone else holding out on me? Okay, let's go ahead and staple these together and I'll show you what I have. Hopefully I've got it right. There, good. Okay, so here's my my graph. So you can see I've got the two curves, and I laid out the you know the scale here just so that we'd all be sort of consistent, and hopefully that didn't throw you because it sticks up pretty high. It's a tall, skinny graph, but anyway, so this kind of brings it back down a little bit. So you have this curve y equals 5x to the sixth, and you have the line y equals 5x, and then this is the axis of rotation. So I guess I didn't label this fully, but this is all that it was asking me to do. It says do this, sketch a rectangle, which I did, the green rectangle. I wrote down the formula just so you see where the formula came from though. I needed to know this distance. That distance is the whole. So that's 5 minus 5x, 5 minus 5x. So that's why this is the way it is. And then the outer rim of this thing is going to be 5 minus 5x to the sixth. So that's why this is the way it is. Getting limits, you probably could figure it out just looking at the graph, but you know, do the algebra, set these two graphs equal to one another. You find that either x to the fifth equals 1 or x equals 0. So x equals 1 or x equals 0 are the two limits, which is kind of obvious if you've graphed it. And then finally, there's my my integral. And all I did was I took this and shoved it into an integral. So it's just to have my limits there. I did do this. I went through the trouble of going through this, and I got 35.478. When I did it on my calculator, just using the built-in integration function, I got 35.96. So I don't know why there's a discrepancy. I must have made a minor error somewhere, but I don't care enough to worry about it. But there it is. So hopefully you did well. We're going to shift our focus, though, from disks to what are called shells. And so let's go ahead and switch gears just a minute. I think I've got it right there. Shell method. So I have this solid that failed last night in terms of its printing. Well, not all of it failed, just the yellow part. So the yellow part is this. I was trying to draw or have this get printed. I was mostly successful. I'll show you in a minute. But this curve, y is equal to 2x minus x squared, that curve rotated around the y-axis gives you, well, it would have given you this, but like I said, I kind of failed midway through. So I guess we'll just have to use this, the one that's already been chopped up. Let me put it here. I'll show you on using my camera. Give me a sec. Let's see, switch to camera land. Where is my camera? There it is. Okay, so there it is. So you can see I'm rotating around this axis right here, and you can sort of see that if this was solid, that's what we'd be interested in. You know, you can kind of get a hint. Yeah, you can kind of see that there's that and this. It just didn't quite make it all the way up. Something went wrong. I was dismayed this morning when I got up and I saw what was on the printer. But nonetheless, let's go back here and talk about this. When we take this, if we were to chop this up the way we've been doing it so far, you would have washers, but those washers, this is the hard part with this one, is what is the distance here? It's going to be a function of, since this is a delta y, the little side is delta y, you would have to have a function of y. So what is that function? So this is delta y, delta y. So in other words, I would have to solve for x as a function of y. And this is a cubic. It is possible to do that. I don't want to, so I'm not going to. But you could, it's not very fun. So doing this with washers is very difficult. But if we chop it up differently, if instead of chopping it up the way that is being suggested here, we chop it up using a vertical rectangle like this, then we're going to get a much different, a better picture, I think. Here, let me just sketch to restart this. So here's this function. Y is equal to 2x squared minus x cubed. Imagine chopping up this thing using these rectangles, which is the way we're most comfortable anyway, and then rotating those rectangles around the x-axis. You're no longer going to have things that look like this. You're not going to get washers. You're going to get these things. Here, I'll show you because I did this. So here, the orange thing did succeed. And so if you can kind of see that this has been chopped into, if I can pull one of these off, sorry. There, that's the first time I've separated those since it came off the printer. But each one of these is like a tube. We call these shells. So there's a shell there, and then you have this shell. And so what we're going to do is, instead of computing the volume using washers like this, we're going to use these shells, figure out the volume of each shell, and then add those up to make the total volume of this thing. So let's just go to it, try to figure out the volume of, and I actually have a bag at home, a big Ziploc 1 gallon bag full of shells for you. Shells, these things. Left it at home though. They're just 1 layer thick. Those of you who are, know what I'm printing, but so they're really, really thin. So you can actually take them and flatten them out. So because I was unsuccessful in doing that, I'm going to have to do this using this. Just see, is there another possible way? I don't think so. Yeah, I'll just do this. So we'll pretend that I brought these in for you, and you could do this. So here, good enough. So each of these shells is like this. It's like a tube, if you will. There's my tube. So here's how we're going to compute the volume of a shell. Is you have to imagine that it has a thickness. Now this is really thin here, this one. These are a little thicker, these rings that I have here. So this one is super thin. And so we'll imagine the, here, where is my PowerPoint? Discard, keep. What's wrong? Did I mess up something? No? Okay. I never know if you're laughing at me or with me. Okay, so here's what one of these shells looks like. You have a delta R, but in our case, the delta R is delta X. So here, I'm going to just draw this right here. So you have this sort of situation. These are really hard to draw. There we go, good enough. Okay, so here, in this case, I'm using delta X. So let me just back up one. So you can see delta X right here. If you imagine this going around the X-axis. So I've got delta X, that's the thickness. Now the hard part with computing this volume of this one shell, so the volume of this thing, is like the formula, like what am I going to do? Am I going to subtract 2 volumes of 2 cylinders? Like there's a smaller cylinder inside a bigger cylinder? That's too complicated. It's way easier to just think in terms of, so we're going to call this the radius of the shell. It's way easier to do this. So let me just show you up here. Here we go. Okay, so what we're going to do is we're going to take that shell and we're going to slice it and flatten it out. And so my strategy is to take the shell, flatten it out, compute the area of this rectangle. I know it's got a corner missing because I'm weird, but you have the rectangle and then multiply by the thickness, which is delta X. So that's the way that we're going to do this. So you have your shell, it's this thing like this. You flatten it out, and there you go. Let's do this up here. So let's see, yeah, here we go. This will do it. So imagine a tin can or a toilet paper tube. If you were to slice it and you flatten this thing out, so you've got this can or this shell, and you flatten it out, the, the height of this thing is the same as the height of the original shell. So however tall this is, that will be this distance from here to here. So that's how high that is. Now, if you remember, we did something like this when we were playing around with the index cards, flipping them around, and you asked you for surface area. To imagine surface area, you just compute the distance along here. So it's the height times the distance along there, which is the distance around this circle. So that's the circumference of this ring. So that's the way this is going to look. This is going to be whatever the height is. So usually it's going to be f of x, the function, but whatever the height is, this is the circumference, which is pi r squared in terms of your, I'm sorry, 2 pi r. I don't know what I'm thinking. 2 pi r. Sorry about that. Okay, so let's actually do this for this problem that we're working on, this one, and then we'll see the formula. So there are formulas for all of these. I'm really not a big fan of a formula, to be honest. Because the point of this is not to memorize a formula, but to understand this sort of the way, because who cares? Honestly, who cares what volume this thing is? You know, what's the big, I mean, you might as an engineer at some point care the volume of some weird shape like this, but I don't know, it just seems so weird. But what is useful is understanding the process that we use, because that's a useful thing. We're going to use it for several other things as well. Okay, so getting back to this, I'm going to need to switch over to Notability because I don't have enough room here, but we'll get this done. Let's put it down here. Let me just redraw. So we've got this. Y is equal to 2x minus x cubed, I believe that was. Let me see. Ooh, where'd it go? Oh yeah, 2x minus x cubed. Okay. Excellent. We're rotating around this axis here. And so the logical thing to do is to make a vertical rectangle delta x. And now imagine that that thing, that vertical rectangle, has been turned into a giant tube. Oh, my giant tube is terrible. Whatever. Okay. Anyway, delta x is the thickness, delta x. The height of the tube is the height of this rectangle, and that height is the function in this case. So once again, it's really important to sort of think through where are we measuring these. I've got another one of these to show you if we have time, where the height is going to be the difference between two functions. So this one, you've got the difference between two functions is the height of each of the rectangles. Now the radius, how far over is this? So how far over does that go? This is the radius. So here, this depends on where that axis is. And the axis happens to be the y-axis. And so the radius happens to just be x. So the height is the function, the radius is x. And so the volume of this ring is going to be 2 pi times the radius times the height times delta x. So just to review, I mean, we're taking this, imagine this thing that I know looks terrible, and actually, for those of you who do 3D printing, I originally printed one of these rings in TPU, and it was way too floppy, but it did look sort of like this. It was just sort of flaccid. And then I did it in a different material. I did PLA, and that was, you could sort of flatten it out. They're all sitting on my kitchen table in a bag now. Oh, well, maybe I'll bring them tomorrow just as party favors. Yes, sir. Oh, it was. Thank you. 2x squared minus x cubed. That would have ruined my entire thing. All right, beautiful. Thank you. Any other? I've gotten the rest. So. Yes. Okay, so but that doesn't change the form of the thing here. Okay, now that we've got that, let's just do what we do, right? We've got one of these rings, and of course, I've got a whole bunch of them here. And so I'm going to add up all of these rings and compute the volume by changing that into an integral. Whoops, that's upside down. Let's see, I did my little dish got printed properly. There we go. There they are. So there they all are. If you want, you can come touch this later if it'll help you to visualize. But there it is. I like this better than the wooden one. Someone bought this decades ago, literally, probably in the 90s, probably for hundreds of dollars. But this is the same idea. You have these rings. This is a parabola. I like my cubic better. So this parabola we could do as well. But anyway, getting back to this, let's set this up. Now we're going to integrate this thing, 2 pi x times 2x squared minus x cubed dx. Oh, I need limits, don't I? Well, I think it's clear that we're starting at x equals 0, but I need to know where we end this. So let's set this thing 2x squared minus x cubed, set it equal to 0. You can factor x squared out of this, and x equals 0 or x equals 2. So that must be x equals 2. We get 0 to 2 of this thing. So does that look all right? Let me make sure there's no questions. This, by the way, this is kind of like what your quiz will look like next time, is you'll get to this stage and I'll be like, yeah, don't bother. I saw some of you did bother, and it's a good thing that I'm not grading that last bit, because some of you don't have the correct answer, even though you have the correct setup. So you should bother, because you will have to do this on the exam, the test in next week. But for now, I just want to get the setup. Hopefully you can learn how to do basic integrals in algebra. Okay, let's just do this though. Since I've got it here, I might as well crank through. So this is going to be, give me a sec, 2 pi, that's 4 pi, let's see, I'll do this, 2 pi times, it's going to be 2x cubed, which will be x to the fourth, 2x to the fourth over 4. And then that'll be x to the fourth, which will become x to the fifth over 5, evaluated from 0 to 2. So what's this end up being? 1632 fourths. So 2 pi times 32 fourths minus 32 fifths, which we all know is going to be 2 pi times 32 over 20. And then, so that's what, 64 twentieths or 32 tenths or 16 fifths, 16 pi over 5. There we go. So that has the volume. So if I had my units, now I got to admit, when I modeled this, so when I modeled this on my computer, I could show you, I could pull it up. But when I modeled this, I used millimeters. I think I had it. Was it 2 millimeters big? I forget. But I scaled the whole thing. So I don't know what scaling factor I used. But so let's see, what is the deal here? N equals 20, scale is, yeah, 20, oh, 30. So the whole thing, I guess that it would be 2 millimeters or 4 millimeters across, but I scaled it by a factor of 30. And so that's why it's 60. Wait, 4 times 120 millimeters across this thing. So yeah, so if I guess you'd have to scale up the volume to 16 pi over 5 times 30 cubed would give you the volume of this thing. Okay, let's do this one, the blue one. So let me explain what this is. So this one, I have the formulas down here. These are 2 parabolae. I will sketch them, and oh, you don't want to see that? You don't want to gawk? Let's see. Why is it not zooming out? There it is. Ooh, beautiful, isn't it? Okay, but anyway, getting back. Let's go back to this. Okay, so I wish this was going around a different axis. I guess we could do this around a different axis just for fun. Okay, so we'll use this, the two functions here, but we'll use a different axis than the y-axis. So these are the two, here's the two curves. We have y is equal to 3x minus x squared over 2, and y is equal to x squared over 2 minus 2x. So those are my two functions. Let's graph these first, and then we'll talk about the axis that we're going to rotate this stuff around. Okay, so the first one, let's see, I need to know where it crosses the x-axis. It'll be easier if I do that. So let's see, this is going to be 6x minus x squared equals 0. So x equals 0 and x equals 6. So 0 and 6. And because that's a negative, this thing will open downward. So you'll have something like this. So that's y equals, this is the value 6 there, y equals 3x minus x squared over 2. I'm sure that's not to scale. Not only that, but it doesn't look right. It's kind of tilted, isn't it? Oh, well. The next one. So y equals x squared over 2 minus 2x. I'll set that equal to 0 just to find out where this is going to intersect with the x-axis. Looks like it's going to intersect at 0, conveniently, and 4. So here's 4. So this thing is going to look something like this. I'll try to do a better job. So there's that one, y equals x squared over 2 minus 2x. It'll be a parabola opening upward. It's not perfect, but good enough. I just want to get a good idea of what this looks like. So I'm going to rotate this around now that I've got these graphed. Unlike what I did here, so just so you know, this one, it's rotated around the y-axis. You can see that. Instead, I think I'm going to rotate this around the line x equals 5, just to make things different, because that appears, at least on my plastic thing here, it appears to be where the two surfaces are intersecting. So we'll hope that that's the case. And I'm pretty sure it is. So I'll put my line, this is my axis. This is the y-axis, by the way. Here's the x-axis. This is the line y equals, no, x equals. This is the line x equals 5. So let's go ahead and take this and rotate it around this axis. So you can see, hopefully, why I'm going to use a vertical rectangle here. If you used a horizontal rectangle, it's just going to be a pain to try to figure out what you're going to be doing. So I'm going to rotate around this. And let me just jot down my, here, I'll first of all do my best to sketch this thing. Wow. Well, doing the best I can. So your sketches probably will be better than mine. Okay, so this here is delta x. That's the small side of the rectangle. I'm going to need to know the radius and the height of this thing. So it's going to be something like this. What is it, time? Oh, we got 5 minutes. We can do it. We'll get it set up. So you've got this thing, this ring. I need to know the height and the radius. So let's do this. The height is the easy one. That's the distance between the purple and the red curve. So the height is going to be purple, which is 3x minus x squared over 2, minus red, x squared over 2 minus 2x. And be careful with the double negatives. So that's the height of this ring, or this shell. Now the radius is the distance from that to this axis, and this axis is x equals 5. So this here is x, so this will be 5 minus x. So here r is 5 minus x. So having a good sketch, oh, and by the way, if you solved this, we'll just pretend you've done the algebra, you do get 5 and 0 as the 2 points of intersection for x. But anyway, if you have a good sketch, it'll go a long way to helping you get a nice, figuring all this stuff out. Now that we've got this, let me just set this up. We're going to integrate from, what are we doing here? From 0 to 5 of 2 pi r h dx in this case. So let's do this. It'll be the integral from 0 to 5 of 2 pi times r times h. It's 5x minus x squared. So I just combined these. So 3x minus negative 2x is 5x, and negative x squared minus x squared, minus x squared over 2 minus x squared over 2 is just minus x squared. I was too lazy to write it all. What do you think, Eli? So the radius is going to be the distance from the ring, if you will, to the center. And so let's go back up to our graph. Here's the center. The axis of rotation is right there. And we want to know, here's the thing that I'm rotating around that axis. And so this distance from here to here is what I want to be able to express. And so you know that the distance all the way from there to the y-axis, that's 5. So this distance from here to here is 5. The distance from here to here is just x, because the delta x, we want everything in terms of x. So that'll be just 5 this minus the x, 5 minus x. So yeah, this is the worst. This is the worst case scenario. So that's why I wanted to make sure that we did one. I know this is easier because it's rotating around the y-axis. Anything else that we need to clear up? All right, I don't think I have the page number for the next homework, but it's there. It's just a bunch of shells. Set them up. That's the main thing. Get them set up, and then if we can get the calculations, that'd be great. But on the quiz next time, I'm just going to have you set them up, or set one of them up, not a bunch of them. So if you want to come look at my shells in closer, you can. Otherwise, we'll see you tomorrow morning. Thanks for coming today on this cold morning. Oh, stopping the recording.